everybody. So I'm Lila. Okay, there we go. Hi, I'm Lila. I am part of the outreach team on ToborTech. We are a team of 15 members, and we this is our 10th year in FTC. Uh, yeah, I guess, and I'll go ahead and introduce our speaker for today. 18225 high definition. Um, and I guess I won't introduce you guys for you. You can go ahead and say what your presentation is and anything else you'd like to introduce about yourself. So yeah, go for it.
My name is Andy Tian. I'm from team 18225 high definition. We're now a fourth year team in Washington, and we have around 14 members, and I lead the mechanical section of the team. So today we're going to be talking about how to design a software integrated robot, and I'll go into details about how to do so and all the kinks that come with this kind of robot, and also what differentiates it from other kinds of robots. So if you guys don't mind, I'll start now. Okay. So obviously the first question we have to answer is how to actually design a software integrated robot. And the simple answer is there is no recipe. Personally, we believe that designs really come from like the people and their ideas. So I don't believe it's right for me to tell you a specific way to build a robot or any specifics that may limit your creativity. Instead, I would like to present a short guideline for everyone that can be used to evaluate your design when you bring your design out, and can also be a good criteria for measuring a design, as beyond the hard performance on paper, there are also many soft aspects of a robot that can cause it to perform well or not so well in a competition. Um, at the very end, there will be a little case study where I'll bring out the past 3 robots that I've worked on, and hopefully we can go together and look at these designs and figure out what went well and what didn't go so well in these designs. And hopefully through learning about this process, you guys will have a better understanding of what it means to make a software integrated robot, and what it means to and how to kind of evaluate how well maybe your design is. So software integrated robots are super, and so they're simple, they're useful, they're pose designed, and they're environmentally resistant. Although these robots may end up looking a lot more complicated, this is the core design principles that we've decided to stick to in our team while we're considering all these designs. And I'll go into detail about why each of these steps is so important, and why each of these aspects matter. So let's first start off with simple, which I believe is arguably the most important aspect of robot design. So why make it simple? So simplicity allows both your hardware and software team to quickly troubleshoot. So whenever you have issues with your design, or whenever you've experienced issues through testing, keeping things simple makes it very easy to find the source of these errors. So in a more complicated robot, there's many different points of failures, and sometimes there's points of failures that not even the designer has considered before. So by keeping the modules simple, and by keeping the modules simple and compact, what you do is you basically minimize the points of failure. So even if something were to go wrong, you'd have an easier time troubleshooting. And keep in mind, because the goal is to create a software integrated robot, this means that you are going to have both software and hardware issues. So you need to be able to quickly differentiate between whether it's a software or whether it's a hardware issue in order to quickly debug. Now, if things were to be more complicated, and then it might seem like a mix of both, which I'll talk about later, which was definitely an error that we made going into the past season. And also talk about what it means for the robot to be complex, because although the mechanisms could seem very simple, the implementation could be a lot more complex. And as we found out, sometimes a simple looking design can be a lot more than we bargained for. So just a few general pointers for keeping it simple. Basically just kind of simplify the mechanical and programming aspects of things. And to do that, the easiest way to do so is to separate everything into small independent modules. So if you can see it on your right, that is our world's robot separated all into its core components, which that being the delivery, the intake, and I just kept the drivetrain and the turret together for the sake of showcasing, but really at its core, it's just a Go strafer chassis with 3 different specific modules attached to it. So what does it mean to be simple? So simplicity not only comes from the simplicity of your hardware components, but also the simplicity of your software components. So not only is it recommended to limit the amount of transfer motions or as I'll talk about later, the transfer times and the poses of the robot. It's also good to limit the degrees of motion that your robot possesses. So although this flexibility can prove very powerful in gameplay, if not implemented correctly, it could also easily come back to bite you. And having so many different things for your robot to control can result in complicated operations and also the dependency on software. So one thing I want to make clear right now is that a software integrated robot means that the software components are very well integrated into the robot, but the robot should not be dependent on software. So no matter how good your software is, there is probably some contingency where that software could fail. And in those cases, it would be best if your robot didn't drop very hard in performance because of a software failure. So so going back to this slide, separating into smaller pieces is a very good design practice, especially in a larger team. So by separating these modules into these 4 individual modules, we were able to develop all these modules parallelly. So not only is their development time shorter, but each of these modules are independently tested. So prior to integration, we know that all the modules work according to their specifications. And integration is simply the act of putting these 4 independent modules together and sending it off to programming for them to write the auto and the teleop. One extra bonus of this modular design principle is basically that in between matches, if any of our modules break, rather than if the breakage is like very severe or if it's an error that we think we can't fix during our downtime, what we can do is we can actually just swap out the whole entire module. And that is not only quick maintenance, but it's also a great safety for our drive team. So they have the confidence to go out there and throw the robot around and actually extract the performance that we can extract from the robot without having to worry about the robot breaking down in the middle. So this goes on to usefulness. So I understand that first really emphasizes on innovation and also emphasizes both on the software and hardware side. But I'd like to suggest that to not make innovations for the sake of adding innovations. So although there might be some really innovative, really complex solution, I'd suggest you take a simpler solution. So oftentimes the simple solution is actually a very innovative one, because by simplifying the problem again and again, you create a very succinct and very beautiful solution. So rather than when you're designing, rather than targeting uniqueness, think of uniqueness that comes with a good design. So rather than trying to think about a specific module in a very unique way, instead think about try different approaches to tackling the problem. And sometimes when you find a better or more optimal approach, your robot will naturally deviate from the standard meta, and it will look unique, so to speak. And one last thing to consider is that 2 minutes of your game is always devoted to teleop. So what this means is that a lot of times, although a very complicated robot could have a very high performance on paper, what this boils down to is how much confidence your drive team has in their machine. I would like to argue that a slightly simpler machine could perform better, not because the mechanisms work or like the mechanisms work so much better, but the drive team is instead very confident in their machine and they know the limits that they can push the machine to. And knowing these limits, sometimes the usability of a simpler machine beats the performance of a more complicated machine simply because the drive team is that much more comfortable with their machine and thus can push it to higher limits. So now that we've talked about usefulness, we talk about poses. So poses is also a very critical design aspect that we always consider. So what poses can be essentially summarized as is the different states that a robot is going to be in throughout its time on the playing field. So as you can see on the top right, we basically look at the different states. So we have like a normal state where the robot is traveling around the field. We have a grasping state for when the robot is grasping a cone, and uh we also have uh we also have a delivery state for when the element is scored on. So poses are very important because they define how your robot moves throughout its duration in the game. And so not only so you have to consider the challenges that the specific game provides. So take power play for example. One of its greatest challenges is basically how do you get from intaking to delivery as fast as possible? Because at the end of the day, your goal is to have a faster cycle time than your opponent. So whenever they score on a specific pole, you can go faster than them and recapture the pole before they have a chance to bring another cone onto the field. Now, with that in mind, from that challenge, we can see the greatest limitation would be the transition time before poses, between poses. And that is also why the second robot we made was performed so much better in teleop than our first robot. So when you're designing, it's very important to consider the poses that your robot will be in and how your robot goes from one pose to the other, because transitioning from these poses is what you're going to be doing around 95% of the time. And if these transitions are not smooth or they're time inefficient, your drive team will end up waiting on these transitions rather than focusing on making strategic calls or reacting to the situation of the game. So by minimizing, first of all, the number of poses that a robot can have and minimizing the transition time between these poses, your drive team's life is significantly simplified. And that means that they have more time to focus on playing the game rather than focus on operating the robot. So I see a question that says, what is the process for determining the necessary modules for each season? And to that I would argue that so this kind of varies year by year. So like last year, there was one simple task which was just put things on the pole. So for that, we basically broke it up into, first of all, obviously you need to intake the cone and deliver the cone, and then so those were the two different modules. So for this year, so the way we tackle modules is basically every function on the field is kind of a module. So like for this year, we have I think 5 different modules. So every capability that your robot will perform is separated into a module. So that way every member can think about one specific task rather than having to worry about the big picture. Um, so once like the whole team comes together and sets the big picture, everyone can focus on a little piece, and then when we put it back together, it will perform as necessary. Does that answer your question? Okay, and then the next question is that do we have 1 or 2 people design and build, or does the entire hardware team help and work with each other to make a module? So we have a 14-member team. So last year with I think 4 different modules, we broke the team down into 3-man teams. So that way everyone, so the smaller the group, the faster they kind of work because there's less communication, negotiation involved. So as a big group, of course, we have to agree on the set direction of the robots, but after we agree on a set direction, what becomes important is to execute these modules very fast and develop them fast enough that both programming has enough time to program an auto and drive team has enough to practice, but also that we have enough time to go through maybe 2 or 3 iterations in between competitions, which will boost our performance. Does that answer your question? So basically the short answer is we break the modules down, and then so the whole team works on the robot as a whole, but each individual module maybe goes through 3 or 4 different people. And then so the 3 different groups they consist of 1 programmer and 2 hardware people. So the way our team works is people specialize, but they also have to do all the tasks. So there's people who spend a little more time programming, and some people spend a little more time on outreach. So usually how the team works is so there's going to be one experienced person in mechanical. So they'll guide the team, and then the more experienced programmer will kind of write the basic test code. And the other person is learning so that over the next year, they can take over as the more experienced member. Does that make sense? So now that we've talked about poses, I want to talk about environment resistance. And this is kind of the most important part of designing a robot. So this also contrasts between performance and on paper performance, because in a sterile environment like your workshop, there's going to be different variations that you can never like anticipate. So it's always good in design to kind of minimize the points of failures that a robot can have. So this goes back. So environmental resistance comes in many forms. So first of all, one of the differences between trying things at your warehouse and kind of going to a competition is, of course, the introduction of 3 other robots. So so what ends up happening is you'll find that anything that extends outside of your robot is probably going to be touched, hit, or they'll meet some kind of stress. Like even with our delivery turret for power play, in one of our qualification matches, we ended up, for some reason, in auto, constantly colliding with the opposing alliance. So we kind of fought over the high junction, and that put a lot of stress on our delivery turret. So the way we design everything is kind of stabilize everything as much as we can. Shafts have bearings supporting them. Programmers like cameras, as we've learned, should point downwards on the field so they aren't affected by the environment around them, and the robot should be a little heavier so it isn't pushed around as much. So and one last thing, of course, is to design with human error in mind, because your drive team, at the end of the day, they're human. So when designing a robot, you have to consider how much error your drive team can have before your robot stops becoming as efficient. And that kind of was the big change or the shift in design philosophy that we experienced, going from states to worlds, was that our robot became a lot more driver tolerant. So we had around 7 inches of tolerance both in the intake and the outtake. So although we strive for precision, at the end of the day, we also have to consider that our drive team is human. So our current design philosophy is basically that we make a robot that is as optimized as possible, so it performs very, very well, but at the same time, it needs to perform very well, not only in a specific circumstance, but in a designated range of circumstances. So say the intake has a large guide, or the delivery has a large guide, or like for the power play season, one of the criteria we set while designing was that the driver had to be able to have around 4 inches of back and forth tolerance when delivering the pixel on the stage or on the backdrop, so that when our drivers get stressed or there's a misinput, our robot doesn't end up crashing into our backdrop and descoring our elements. So to summarize, kind of the important parts is that your robot has to be tolerant both on the software side and on the hardware side to the things that can happen. And the things that happen are A, changes in lighting, B, changes in interactions between robots, like maybe someone decides to hit you, someone decides to ram you, and 3 is different states that your drive team could be in, like maybe they're just a little jittery today and they make a lot more misinputs. And now we go to a question that says, earlier you said that you brainstorm and allocate members to narrow in on specific modules. Do you ever have any issues later with the iteration process and putting all the modules together? If so, what do you do to overcome it? So in our design process, so before we actually break things down into specific modules, the first thing we'll do is kind of set the criteria for each module. So that not only includes how the module should perform, like maybe I wanted to intake 2 pixels at once and give me the 2 pixels to my delivery. It also includes static things, so static interfaces between the different modules that cannot be changed. So basically, when we go into these modules, the whole team has kind of idea about how the robot will look like, and we're all kind of working towards that shared vision. But in order to accomplish everything and have integration work out, the key thing to do is to put very concrete, very static what's it called, specifications for each module. So that way, delivery, as long as they fit within their criteria, they should be able to interface with the transfer system. And that is going to help us a lot with putting all of the modules together. And the iteration process, once again, is based off of all these specifications. So if, let's say, delivery team figures out that they need a little more space, we have to kind of talk with all the other sub teams to make sure that this change isn't going to affect their product. So I guess the way we overcome these integration issues is, before we even start designing, we set very clear boundaries for each module about how they're going to interact with each other. And of course, what kind of space they're going to take up on the robot and how many motors or servos they can use. Does that answer your questions? Okay. So now that we've kind of understood, or like we've kind of seen all the criteria, let's go over the three robots that I've helped develop, and let's see how each of them play into um the criterion that I suggested. So these three robots respectively are our freight frenzy robots, our first power play robot, and our second power play robot. So how this is going to work is I'm going to show you a small clip of our robot actually scoring, and from that I hope to I hope you guys can send in the chat different points of failure that you think could happen. So what can go on to disrupt the scoring process of it, and what you think the limitations of each design are. So let's go ahead. The first one will be our power play robot from Worlds. So here is a video of us scoring. So as you can see, the driver intakes from the stack, and then it places it onto the delivery before the delivery extends out, and places it onto the high junction. So it kind of looks something like that, and then it pulls back, and then your cone is successfully delivered. On your right are some other different pictures. So I'll give you guys around 2 or 3 minutes. Feel free to send, first of all, any points of failure that you think could happen, and also how well you think it adheres to all the other principles of, first of all, simplicity, usefulness, and environmental resistance. Right, thank you to everyone who contributed. So let's go over some of these points of failures, and I'll talk about how we work to mitigate them. So the first one was that would be super easy to get hit while getting extended. So there are two different factors that play into our consideration with this. So first of all, that's the reason we chose to run two slide sets rather than one, because we felt that with two slides there'd be less of a chance that these slides would break from an impact. And the second thing is that the robot is protected while delivering, so that was less of a concern in the power play season compared to the other seasons. The second one is the extension may be knocked out of place when attempting to deliver. So once again, that is resolved simply by the season criteria. And the next point that is brought up is transfer being a point of failure. And so transfer was certainly a point of failure for this robot. So the main thing was that the cone could, depending on how high we grasped it, it could have a little wiggle room. So how we adapted to that is if you look on the rightmost picture, you can see there's actually a color sensor mounted on the delivery. So rather than beyond like refining the mechanism so that the cone has a lot more tolerance during the transfer, we also added a software or we also added some sensors to help us basically know if a cone was successfully transferred. So what that looked like in auto was basically if we somehow missed a cone during auto, and after the robot went through its delivery motion and we found out and our robot checked the sensor and saw that the sensor still read that there was no cone there. What we would do instead of going to deliver, we'd simply repeat the intake task again until we ultimately got a cone, or until if after repeated failures, we just simply go and park and assume that it was a mechanical failure. The last one is that the extender could accidentally drag the pole down all the way. So that is certainly a point of failure. And we mitigated that by simply by wrapping the delivery guide all the way around the slides. So that way there wasn't much space between the slide and the guide board. And so that prevented the pole from getting caught inside the guide board. And if the pole was caught under the guide board, simply pulling back would kind of capitalize on the elasticity of the pole, and the pole would fling back into the correct position. So now we're going to go into our states robot. So this is a cycle from one of our qualification matches during states. So as you can see, it's a giant arm that swings around and grabs something, and then it uses vision to align with a pole and to grab. So once again, I'll give you guys 3 minutes. Once again, what are the points of failures and how does it adhere to our other principles? All right, so thanks to everyone who contributed. Now let's go through all the suggestions. So the first one is that environmental interference with camera vision. And that was certainly one of our biggest problems and why we decided to drop the design in favor of the design you previously saw. And so basically what ended up happening was, since the camera was not looking down to find the pole, it was looking kind of sideways. On one side of the field, you saw that we had purple and yellow spotlights, so that kind of interfered with our computer vision, and that was kind of part of the reason why our robot would be very slow at delivery. The second one is damage of the arm from people running into it. That was certainly a concern going into states. So, but the way we mitigated that was, instead of going straight from intake to a delivery position, instead we go from intake to a neutral position and then go to a delivery position. And so this allowed us to stay within our 18 by 18 perimeter during match movements, so that prevented people from hitting our arm. And then, of course, as someone correctly pointed out, it isn't sticking to the goal of minimal movement. So this impacted us both during our autonomous period and our teleop period, because the drastic motions of the arm were, first of all, slow, but second of all, because the mechanism was so big, we ended up kind of shifting ourselves throughout the duration of autonomous period just due to the swinging of the arm. And of course, there is definitely possible damages from grabbing and delivering onto a pole. So we found that we kind of were at a bottleneck where if we wanted to go faster, we always had to wait for the arm to retract back into the neutral position before we could ensure that there was no damage to the machine while we were using it. And yeah, and then the last one was that there were a lot of joints to actuate in order to perform a motion. And so that was also a lot of valuable time that we would waste during our teleop period. So now finally, let's go on to our freight frenzy robot. So here is our freight frenzy robot. It's just on the bottom right. This is our it's just a recording of our autonomous. So once again, I'll give you guys 3 minutes and then point out any points of failure you guys see and evaluate how it goes with the different principles. So the question was, how many times did our horizontal sliders get hit? So for this robot, I don't think, for the Freight Frenzy robot, our horizontal slides didn't get hit very often because the playing field was kind of separated into 2 sections. So it was very rare that the blue alliance would come over to the red side and vice versa. For our power play robots, during the world competition, we in think in semifinals we did hit Vertex the um during the thing. And the question was, what do you use for wire management? So we basically ran kind of like a closed hanger system on our retraction string. So if you look to the top right, there's a bunch of little loops of wire, and as that string extends, the wire would naturally extend itself to come with it. And as the string retracted, the wires would naturally fall back into their place designated by the little coat hangers. Right, so thanks to everyone who contributed. So the point I'm seeing is that a lack of computer vision assistance could make it harder to score on the Alliance Hub. So we didn't actually use computer vision for scoring on the Alliance Hub. Instead, we basically had the extension at a set angle, so all the driver had to do was drive until it's kind of aligned, and then the cup would close the rest of the distance. A lack of computer vision thankfully didn't impact our intaking that much either. And then so basically the claw could turn 90 degrees. So if we were without vision, it'd still have a lot of tolerance and was able to successfully intake freight. So for the last season, how did we manage our wires with our vertical sliders? So one of our main design considerations for that and how we kind of limited the room for error in our robot is actually, if you look, there's no wires on the delivery. So the delivery is a completely passive delivery. So that not only mitigated the need for wire management, but it also kind of prevented the wires on the delivery from getting caught on anything during the delivery process. So that's all I have for today. Thank you so much for listening.
Thank you so much. That was really great. That was actually really interesting. I guess now we just have to wait if anybody has any more questions. Um, and if not, I guess we're all done for the day. Thank you so much for hosting, Andy. I really appreciated that. It was great.
Thank you for hosting me.
Yeah. All right. I think we don't have any more questions. So, oh yeah. Do you want to drop your team's Instagram or any social media that you have? You can drop it in the chat or you can just say it.
Yeah, sure. So yeah, feel free to follow us at I think FTC 18225 at FTC 18225. And if you guys have any questions, feel free to email us. Um, I think if you just Google us, well, there's a team website and you guys can learn more. We have some other reference materials if you guys need, and yeah, that's about it.
Okay. Awesome. Thank you so much. Have a great day.
Thank you so much. Bye.